Right now, the atoms in your body are doing something extraordinary simply by existing, not by moving, not by thinking, not by participating in the biological processes that constitute your life, simply by being matter, by being the specific configuration of protons, neutrons, and electrons that constitutes a physical object in the observable universe. They are participating in one of the deepest unsolved problems in all of science. They should not be here. Not in the sense that your existence is improbable, though it is. In the sense that the physics governing the creation of atoms permits, and in fact demands, the simultaneous creation of an equal number of objects that are the precise inverse of every atom you contain. Objects that upon contact with any atom in your body would annihilate it completely, converting both into a flash of pure energy and leaving nothing behind. These objects are not hypothetical. They have been created in laboratories. They have been stored, studied, and measured. They obey the same laws of physics as the atoms in your body, with one difference. Their charge is reversed. Their internal quantum numbers are the mirror image of ordinary matter. A proton in your body has a positive charge. Its antiparticle, the antiproton, has a negative charge and identical mass. An electron in your body has a negative charge. Its antiparticle, the positron, has a positive charge and identical mass. They are not exotic. They are the precise, mathematically necessary complements of everything you are made of, and they should exist in equal abundance to the matter you are made of. The laws of physics that govern the creation of particles in the Big Bang are, to an extraordinarily high precision, symmetric between matter and antimatter. They do not prefer one over the other. They do not have a built-in bias toward the configuration of the universe you inhabit. The mathematics says that for every particle created, an antiparticle should have been created with it. The mathematics says that when the universe cooled enough for annihilation to begin, every particle should have found an antiparticle and disappeared. The mathematics says the universe should be empty. It is not empty. You are in it. And for 13.8 billion years, no one has been able to provide a complete and verified explanation of why. This is the antimatter problem. And it is not a philosophical curiosity or a metaphysical puzzle existing only at the edges of human knowledge. It is an experimental crisis at the center of particle physics, because every experiment ever devised to measure the properties of antimatter has found them to be identical to the properties of matter, to the precision of the measurement. The symmetry is not approximate. It is exact to every decimal place physics can reach. If the symmetry is exact, the universe should not exist. If the symmetry is broken, the break has so far been invisible, until now. The alpha experiment at CERN, whose full name is the Anti-Hydrogen Laser Physics Apparatus, has spent years doing something that should not be possible. It has created atoms of antihydrogen, the simplest antimatter atom, consisting of an antiproton orbited by a positron. It has trapped those atoms in a magnetic bottle, preventing them from touching the ordinary matter walls of the apparatus and annihilating. It has held them long enough to study them, and in its most recent publications, it has performed measurements of antihydrogen's response to light, to gravity, and to fundamental quantum transitions, measurements that are the most precise ever achieved for any antimatter system. What the alpha experiment is looking for is a difference, any difference, any measurement of antihydrogen's properties that deviates by any amount from the corresponding property of ordinary hydrogen. Because if matter and antimatter are truly identical in every physical property, then the universe is unexplained. And if they differ, even slightly, even in a way that has so far evaded every previous measurement, then the difference is the fingerprint of whatever process tilted the universe toward matter in its first moments. The most recent results are the closest physics has ever come to finding that fingerprint. What they reveal and what they imply is the subject of this account. The core question is this: if the most precise measurements ever made of antimatter reveal it to be identical to matter in every observable property, what does that tell us about why you exist? There is no comfortable answer, but the precision of the question has never been higher. Follow it. The mirror. The physics requires. Every physical law you have ever encountered is a statement about symmetry. The law of conservation of energy says that the total energy of a closed system does not change over time, which is a statement that the laws of physics are symmetric under time translation, that they are the same tomorrow as they are today. The law of conservation of momentum says that the total momentum of an isolated system is constant, which reflects the fact that the laws of physics do not change from one location in space to another. Every conservation law in physics corresponds, through a deep mathematical theorem called Noether's theorem, to a specific symmetry of the physical laws. Symmetry and conservation are not merely related. They are two ways of describing the same underlying structure. Among the symmetries of physics, there is one that concerns the relationship between matter and antimatter, and it is called CPT symmetry. CPT stands for charge conjugation, parity transformation, and time reversal. Each letter represents a specific mathematical operation applied to the description of a physical system. Charge conjugation, C, replaces every particle with its antiparticle, reversing its electric charge and other intrinsic quantum numbers. Parity transformation, P, reflects the spatial coordinates of the system, replacing every left-handed process with a right-handed one. Time reversal, T, runs the equations of motion backward in time. Individually, each of these symmetries can be violated. It was discovered in 1956 and confirmed experimentally in 1957 that the weak nuclear force violates parity. It treats left-handed particles and right-handed particles differently. This was one of the most shocking results in the history of physics. The universe, at the level of fundamental forces, has a handedness. It is not symmetric between left and right. Similarly, the combination of charge conjugation and the parity, CP symmetry, is violated in the decay of certain particles like kaons and B mesons. The universe is not perfectly symmetric between matter and antimatter in the behavior of these particles. But CPT symmetry, the combination of all three transformations together, is believed to be exact. This is not merely an assumption, it follows from the mathematical foundations of quantum field theory, specifically from the fact that any relativistic quantum field theory that satisfies the requirements of Lorentz invariance and locality must be invariant under the combined CPT transformation. This theorem, called the CPT theorem, is one of the most fundamental results in theoretical physics. Violating CPT symmetry would require abandoning not just one assumption, but the entire framework of relativistic quantum field theory on which the Standard Model is built. The CPT theorem has a specific and testable consequence for antimatter, because CPT symmetry is exact, and because C and P symmetries are individually broken, while CP symmetry is also slightly broken, the T symmetry must also be slightly broken in exactly the right way to compensate. But the more direct consequence for antimatter is this. The CPT theorem predicts that every particle and its antiparticle must have exactly equal mass, exactly equal lifetime, and exactly equal magnitude of charge. Not approximately equal, exactly equal. Any measured difference would constitute a violation of CPT symmetry, and such a violation would require physics beyond quantum field theory itself. The alpha experiment is testing this prediction with antihydrogen. By measuring the properties of antihydrogen atoms with increasing precision, it is testing CPT symmetry at the level of atoms and quantum transitions, scales never previously accessible to antimatter measurements. Every measurement that confirms the equality of hydrogen and antihydrogen properties confirms the CPT theorem and deepens the mystery of why matter dominates the universe. Every measurement that finds a difference would overturn one of the most fundamental predictions of modern physics. So far, alpha has found no difference, and the precision with which it has found no difference is itself the most important result in this field in a generation, because the precision matters. The precision is how close to the truth we have come, and the truth, whatever it is not yet fully visible. But the instrument looking for it has never been sharper. What antihydrogen actually is and why creating it is extraordinary. Hydrogen is the simplest atom in the periodic table. It consists of one proton carrying a positive charge, around which one electron, carrying a negative charge, orbits at a distance governed by the laws of quantum mechanics. The proton and the electron attract each other through the electromagnetic force. The electron does not spiral into the proton because quantum mechanics forbids it. The electron exists in a specific energy, eigenstate, the lowest available energy level, called the ground state, in which it occupies a probability distribution around the proton without a classical trajectory. The hydrogen atom is stable. It is the most abundant atom in the universe. It is the starting material from which all other atoms were ultimately built through stellar nucleosynthesis. Antihydrogen is the precise antimatter counterpart of hydrogen. It consists of one antiproton carrying a negative charge, around which one positron carrying a positive charge orbits. The antiproton and the positron attract each other through the same electromagnetic force that governs ordinary hydrogen. The positron occupies the same quantum mechanical energy states governed by the same equations as the electron in ordinary hydrogen. The antihydrogen atom is by the CPT theorem predicted to have exactly the same mass, the same spectral lines, and the same response to fields as ordinary hydrogen. The creating antihydrogen in a laboratory is not a simple matter of combining an antiproton with a positron. Both must be produced separately, confined without annihilating on ordinary matter, and brought together under conditions that allow them to bind. The antiprotons are produced by firing protons from the proton synchrotron accelerator at a metal target at nearly the speed of light. The collisions produce a spray of particles, including antiprotons, which are separated from the other debris by magnetic fields and fed into a storage ring called the antiproton decelerator, where they are slowed from nearly the speed of light to velocities manageable for trapping. The slowed antiprotons are then transferred to the alpha apparatus. The positrons come from a different source. A radioactive sodium-22 source emits positrons through the decay of its protons into neutrons, releasing positrons and neutrinos in the process. These positrons are collected, cooled, and transferred to the alpha apparatus. In the apparatus, the antiprotons and positrons are brought together and allowed to combine. The combination is not guaranteed. The relative velocities and densities of the two populations must be precisely controlled to maximize the probability of binding. Even under optimal conditions, the production rate of antihydrogen atoms is modest, measured in tens to hundreds of atoms per experimental run. Once formed, antihydrogen atoms must be prevented from touching the walls of the apparatus, which are made of ordinary matter. The contact would result in immediate annihilation of both the antihydrogen atom and the matter in the wall at the point of contact, releasing gamma rays that would be detected but would end the measurement. The confinement is achieved by the magnetic moment of the antihydrogen atom. An antihydrogen atom in its ground state has a small magnetic moment arising from the spin of its constituent particles. If this magnetic moment is oriented correctly, the atom will be attracted toward regions of lower magnetic field strength, and a carefully shaped magnetic field can create a minimum in field strength at the center of the trap, confining the atom there without physical contact with any material surface. The trap does not hold antihydrogen indefinitely. The trapping is imperfect, and antihydrogen atoms escape the magnetic minimum and annihilate on the trap walls over timescales of seconds to minutes. Each annihilation event is detected, providing a record of how many antihydrogen atoms were confined at any time. By measuring properties of the antihydrogen atoms while they are confined, alpha extracts the most precise measurements of antimatter properties ever achieved. The apparatus is an extraordinary achievement of engineering, physics, and experimental ingenuity, and what it is finding, measurement by measurement, is that antihydrogen behaves exactly as hydrogen does, at a level of precision that is now approaching the limits of atomic physics. The spectral lines of the mirror world, when light at a specific wavelength strikes a hydrogen atom in its ground state, the atom can absorb the photon and transition to a higher energy level. When the atom subsequently relaxes back to the ground state, it emits a photon at the same wavelength. These transitions occur at very specific, precisely defined wavelengths determined by the energy differences between the quantum states of the hydrogen atom. The pattern of wavelength at which hydrogen absorbs and emits light is called its spectrum, and it is one of the most precisely measured quantities in all of physics. The most precisely measured transition in hydrogen is the 1s to 2s 2-photon transition, in which two photons working together drive the atom from its lowest energy state, the 1s state, to the second lowest, the 2s state. This transition has been measured in ordinary hydrogen with a precision that exceeds 14 significant figures, making it among the most precisely known quantities in science. The measurement uses laser spectroscopy, a technique in which a laser of a precisely controlled frequency is directed at the hydrogen atoms, and the absorption is detected by monitoring the population of atoms in the excited state. By scanning the laser frequency and identifying the precise frequency at which maximum absorption occurs, the transition frequency can be determined with extraordinary accuracy. The alpha experiment has performed the same measurement on antihydrogen. This is a feat of experimental physics, so technically demanding that describing its complexity in full would require an account as long as this entire script. The trapped antihydrogen atoms, confined in the magnetic trap for several seconds, are illuminated by laser light at the frequency corresponding to the 1s to 2s transition. If the antihydrogen absorbs the light and transitions to the 2s state, it can subsequently reach states from which it is no longer confined by the magnetic trap, and it escapes and annihilates on the trap walls. The annihilation events are detected by scanning the laser frequency and measuring the rate of annihilation events as a function of frequency. Alpha identifies the resonance frequency of the 1s to 2s transition in antihydrogen. The result, first published with meaningful precision in 2016 and subsequently refined in publications through 2023, is that the 1s to 2s transition frequency in antihydrogen is equal to the corresponding frequency in ordinary hydrogen, to a precision of approximately 2 parts in 10 to the power of 12. This is not a small number. It means that if the two frequencies differ, the difference is less than 2 millionths of a millionth of the total frequency. It is a test of CPT symmetry at a level of precision that surpasses every previous antimatter measurement by orders of magnitude. The result shows no difference. Antihydrogen absorbs light at exactly the same frequency as hydrogen, to within the experimental precision. The mirror world, at the level of atomic spectroscopy, is indistinguishable from the world it mirrors. The implications are significant in both directions. If a difference had been found, it would be evidence of CPT violation, the first in the history of physics, and the potential clue to the origin of the matter antimatter asymmetry. Because no difference was found, the CPT theorem is confirmed at a new level of precision, and the mystery of why matter dominates the universe is not resolved by atomic spectroscopy alone. The measurement eliminates one possible resolution to the mystery and raises the bar for any future resolution. The fingerprint of the symmetry breaking that produced the matter-filled universe you inhabit is not visible at the precision currently achievable. The search must continue at higher precision, or in different observables, or in different physical systems. What alpha has achieved is not a failure to find the answer. It is a precise delineation of where the answer is not. And that delineation is itself one of the most important results in fundamental physics in the past decade. The hyperfine structure and the most delicate internal clock atoms are not structureless objects. The particles they contain have internal degrees of freedom, properties beyond their position and velocity that interact with each other and with external fields in ways that create a rich internal structure. The most important of these internal properties for the question of matter antimatter symmetry is spin. Both the proton and the electron in a hydrogen atom have spin, an intrinsic quantum mechanical, angular momentum. The spins can be aligned with each other or opposed. These two configurations have slightly different energies because the magnetic moments associated with the spins interact. The energy difference between the spin-aligned and spin-opposed configurations of the ground state hydrogen atom produces a transition at a specific frequency, approximately 1.42 GHz, corresponding to a wavelength of 21 centimeters. This transition, called the hyperfine transition, is one of the most precisely measured quantities in physics and one of the most consequential. The 21 centimeter line of hydrogen is a primary tool of radio astronomy used to map the distribution of neutral hydrogen throughout the Milky Way and in other galaxies. The frequency of 1.42 GHz is so precisely known and so universally characteristic of hydrogen that it has been proposed as a cosmic beacon, a frequency that any technological civilization in the galaxy might use to communicate across interstellar distances, because any civilization advanced enough for radio astronomy would know it. It was used in the design of the Pioneer plaque, the gold-plated message sent aboard the Pioneer 10 and 11 spacecraft as a potential communication to extraterrestrial civilizations, to define a unit of length through the wavelength of this transition. In antihydrogen, the corresponding hyperfine transition should occur at the same frequency, 1.42 GHz, if CPT symmetry is exact. The antiproton and the positron in antihydrogen have spins with exactly reverse signs compared to the proton and electron in hydrogen. But the energy difference between spin-aligned and spin-opposed configurations depends on the magnitude of the magnetic moments involved, not their signs, and the magnitudes are predicted to be identical by CPT symmetry. Alpha has measured the hyperfine transition in antihydrogen by applying microwave radiation at frequencies near 1.42 GHz to trapped antihydrogen atoms and monitoring the response. When the microwave frequency matches the transition frequency, the atoms that are confined in the magnetic trap due to their spin orientation are driven to the opposite spin orientation, which is not confined by the trap, and they escape and annihilate. The resonance frequency is identified by scanning the microwave frequency and finding the peak in annihilation rate. The measurement has been performed and refined across multiple publications. The result is that the hyperfine transition frequency in antihydrogen is equal to that in ordinary hydrogen, to a precision of better than a few parts in 10 to the power of 9. Again, the symmetry holds. The most delicate internal clock of antihydrogen ticks at the same rate as that of hydrogen. The two atoms, one made of matter and one made of antimatter, respond identically to the microwave probe. The measurement of the hyperfine transition provides an independent test of CPT symmetry from the 1s to 2s transition measurement. The two tests are sensitive to different combinations of fundamental constants and different aspects of the CPT invariance of the atom. Finding agreement in both is a more stringent and more comprehensive test than either alone, and both find the same result. Hydrogen and antihydrogen are, to the precision of the measurements, identical. The precision is extraordinary. The mystery is unresolved. And the unresolvedness is now more precisely characterized than at any previous point in the history of science. Gravity and the question that should have been simple, For most of the history of physics, gravity was assumed to act the same way on antimatter as on ordinary matter. The reason for this assumption was simple. The equivalence principle, one of the foundational principles of general relativity, states that all objects fall with the same acceleration in a gravitational field, regardless of their composition. This principle has been tested to extraordinary precision for ordinary matter in various forms. Neutrons fall at the same rate as protons. Electrons fall at the same rate as neutrons. Objects made of iron fall at the same rate as objects made of carbon. The equivalence principle holds for all matter, tested to better than 1 part in 10 to the power of 13. But antimatter had never been tested. Not directly. The reason is practical. Antimatter is extremely difficult to produce, store, and study without it annihilating on ordinary matter. For decades, the question of how antimatter falls in a gravitational field, whether it falls down like ordinary matter, falls up away from the Earth, or falls at some different rate, was genuinely unanswered by direct experiment. Theoretical arguments from CPT symmetry strongly predicted that antimatter falls identically to matter. If antimatter has the same mass as matter, as CPT symmetry requires, and if the equivalence principle holds, then it must fall at the same rate. But the argument rested on assumptions, and physics has been surprised before by assumptions that turned out to be wrong. The Alpha G experiment, a dedicated extension of the Alpha apparatus, designed specifically to measure the gravitational behavior of antihydrogen, produced its first results in 2023. The experiment works by creating antihydrogen atoms, trapping them magnetically, uttered and then slowly reducing the strength of the magnetic trap. As the trap weakens, the antihydrogen atoms begin to escape. Whether they escape preferentially upward or downward, against or with the direction of Earth's gravitational field, indicates whether gravity acts on antihydrogen attractively, as it does for ordinary matter, or repulsively. The result was unambiguous. Antihydrogen falls downward in the direction of Earth's gravitational field, with an acceleration consistent with the acceleration of ordinary matter. The measurement was not yet precise enough to test whether the acceleration is exactly equal to that of ordinary matter, the full test of the equivalence principle for antimatter. But it definitively ruled out the possibility that antimatter falls upward or is gravitationally repelled. The gravity attracts antihydrogen toward Earth, just as it attracts ordinary matter. This result was expected on theoretical grounds. Its importance lies not in the theoretical surprise, which was absent, but in the experimental confirmation, which was real. For the first time in the history of science, the gravitational behavior of an antimatter atom was directly measured. The result confirms that general relativity, the theory of gravity, applies to antimatter in the same way it applies to ordinary matter. And it eliminates one of the proposed explanations for the matter-antimatter asymmetry, the idea that gravitational repulsion between matter and antimatter in the early universe might have separated them, allowing them to exist in separate regions rather than annihilating. Gravity does not repel antimatter. The early universe would have treated matter and antimatter identically under gravity. Whatever caused the separation, gravity was not it. The measurement of antihydrogen's gravitational behavior is a landmark in experimental physics not because it overturned expectations, but because it confirmed them at a level of directness and precision that was previously impossible. The equivalence principle now applies to antimatter by direct measurement, not merely by theoretical inference. And the frontier of the test has moved to a more precise determination of whether the acceleration is exactly equal to that of ordinary matter, a measurement that alpha G is designed to achieve with future data. The Lyman alpha line and light from the anti-world. The Lyman alpha transition is the most luminous emission line of hydrogen in the ultraviolet. Thus it corresponds to the transition between the first excited state, the 2p state, and the ground state, the 1s state, and it produces a photon at a wavelength of 121.6 nanometers. In astrophysics, the Lyman alpha line is ubiquitous. It appears in the spectra of almost every object containing hydrogen, from quasars to gas clouds to stellar atmospheres, and it is one of the primary diagnostics of the physical conditions in astrophysical plasmas. Its wavelength is known with extraordinary precision. Its transition rate, the rate at which an excited hydrogen atom emits a Lyman alpha photon, is one of the most precisely calculated quantities in quantum electrodynamics. Measuring the Lyman alpha transition in antihydrogen presents extraordinary technical challenges because the photon wavelength of 121.6 nanometers falls in the vacuum ultraviolet, then the spectral region where conventional optical materials like glass and quartz are opaque. Producing, directing, and focusing laser light at this wavelength requires specialized techniques and materials that were not available to the alpha experiment in its earlier phases. The development of vacuum ultraviolet laser sources and optics suitable for use in the alpha environment was a major technical undertaking that occupied years of experimental development. The measurement of the Lyman alpha line in antihydrogen would provide several important results. First, it would offer an independent measurement of the 1s to 2p energy difference in antihydrogen, complementing the 1s to 2s two-photon measurement. The 1s to 2s measurement is extremely precise, but involves a two-photon process that is technically complex. The Lyman alpha measurement involves a single photon and is conceptually simpler, though technically more demanding in terms of laser development. A precise comparison of the 1s2p energies in hydrogen and antihydrogen would test CPT symmetry through a different transition and a different combination of fundamental constants. Second, the measurement of the transition rate of the Lyman alpha line in antihydrogen, the rate at which excited antihydrogen decays from the 2p state to the ground state, tests a prediction of quantum electrodynamics with antihydrogen. Quantum electrodynamics predicts the transition rate with extraordinary precision for ordinary hydrogen. CPT symmetry predicts that the same rate applies to antihydrogen. If the measured rate deviates from the prediction, it could indicate either a violation of CPT symmetry or a breakdown of quantum electrodynamics in the antimatter sector. Alpha has reported progress toward the Lyman alpha measurement and has produced preliminary results consistent with the expected transition, though the precision achieved so far is substantially less than that of the 1s to 2s measurement. The technical development of the required laser systems is ongoing, and future measurements are expected to achieve higher precision The Lyman alpha measurement represents the next frontier in alpha's spectroscopic program, extending the test of CPT symmetry to a new transition and a new physical observable. The significance of measuring the spectrum of antihydrogen across multiple transitions extends beyond the individual results. Each transition tests a different combination of the fundamental constants, including the antiproton to positron mass ratio, the fine structure constant, and the QED corrections to the energy levels. A set of consistent measurements across multiple transitions provides a more stringent and more comprehensive test of CPT symmetry than any single measurement. And if, at some future level of precision, a discrepancy were found between any measured transition in antihydrogen and the corresponding transition in hydrogen, the pattern of discrepancies across multiple transitions would provide theoretical clues to the source and character of the CPT violation, clues that could point toward the new physics responsible for the matter, antimatter asymmetry. The production problem: making antimatter in sufficient quantities. One of the most persistent practical limitations of antimatter research is the extraordinary difficulty of producing antimatter in useful quantities. This limitation is not merely inconvenient. It defines the precision achievable by experiments like alpha and sets the timescale on which progress in the field occurs. Understanding the production problem is essential to appreciating why the alpha measurements, impressive as they are, represent only a beginning, and why the path to definitive answers is measured in decades rather than years. In nature, antimatter is produced continuously in high-energy processes. Cosmic rays, streams of energetic particles originating from astrophysical sources like supernova remnants and active galactic nuclei, they strike the upper atmosphere and produce particle-antiparticle pairs in the resulting collisions. Radioactive decay of certain isotopes produces positrons. The decay of neutral pions, produced in cosmic ray interactions, produces gamma rays energetic enough to create electron-positron pairs when they interact with matter. Antimatter is not exotic in the sense of being absent from the natural world. It is produced constantly, in small quantities, wherever high-energy processes occur. But producing antihydrogen atoms in quantities sufficient for precision spectroscopic measurement requires a controlled and sustained source of both antiprotons and positrons at the energies and densities needed for the combination process. The current CERN antiproton production and deceleration chain from the proton synchrotron to the antiproton decelerator that produces approximately 10 to the power of 7 antiprotons per pulse at intervals of about 90 seconds. Of these, a fraction survive the transfer to the alpha apparatus and are cooled to energies low enough for trapping. Of the antiprotons that reach the trapping region, only a fraction combine with positrons to form antihydrogen atoms. And of those, only a fraction are formed in the ground state, with the magnetic moment orientation required for magnetic trapping. The resulting number of trapped antihydrogen atoms per experimental run is typically between 10 and a few hundred. Each measurement requires multiple runs to accumulate sufficient statistics. The 1s to 2s transition measurement to the precision reported in published results required hundreds of experimental runs spanning multiple years of operation. The precision of the measurement is ultimately limited by the number of atoms available. because statistical precision improves only as the square root of the number of measurement events. Increasing the number of trapped antihydrogen atoms would directly improve the achievable precision. Several approaches are being pursued. The extremely low energy antiproton ring, ELENA, a new deceleration ring added to the CERN antiproton complex, decelerates antiprotons to even lower energies than the existing antiproton decelerator, substantially increasing the fraction that can be captured in penning traps for subsequent use. The commissioning of ELENA has already improved the antiproton supply to experiments like ALPHA. On the positron side, improved positron sources and more efficient positron cooling techniques are being developed. The combination of more antiprotons, more positrons, and more efficient combination processes is expected to increase the number of trapped antihydrogen atoms per run by significant factors over the next decade. This increase will directly translate into improved measurement precision, pushing the test of CPT symmetry deeper into the parameter space where, if the symmetry is violated at a level relevant to baryogenesis, the violation might become visible. The production problem is not an insurmountable barrier. It is an engineering challenge being actively addressed, and the trajectory of progress suggests that the precision of ALPHA's measurements will continue to improve substantially over the coming years. The question is whether the precision can be pushed far enough, fast enough, to find the difference that the universe's matter-dominated state implies must exist somewhere. What the positronium experiments reveal. Positronium is a bound state that is entirely composed of antimatter and matter in equal parts. It consists of an electron and a positron orbiting each other, held together by the electromagnetic attraction between their opposite charges. It is, in a sense, the simplest possible atom, consisting of two elementary particles with no nuclear component. It is also fundamentally unstable. The electron and the positron orbit each other until they overlap sufficiently for annihilation to occur, releasing 2 or 3 gamma-ray photons, depending on the spin configuration. Positronium exists for only a brief time, which burn from approximately 125 picoseconds for the singlet state to approximately 142 nanoseconds for the triplet state before annihilating. Despite its brief existence, positronium can be created in the laboratory in sufficient quantities to study its spectroscopic properties, and its quantum mechanics is described with extraordinary precision by quantum electrodynamics. The energy levels of positronium, the frequencies of its optical transitions, and the rates of its annihilation are all calculated with high precision and tested against experiment. Positronium is an important testing ground for quantum electrodynamics, precisely because it contains no hadrons, no protons or neutrons, and is therefore a cleaner theoretical system than hydrogen, where the finite size and internal structure of the proton introduce theoretical complications. The spectroscopy of positronium is relevant to the matter-antimatter problem, because positronium is composed of equal amounts of matter and antimatter, and therefore provides a direct test of the symmetry between them. The laws governing a hydrogen-like atom consisting of a positron and an electron must be the same as the laws governing any other electromagnetic bound state by CPT symmetry. The measurements of positronium's energy levels and transition frequencies test the consistency of quantum electrodynamics applied to a system that contains both matter and antimatter, and that exists only briefly before the two annihilate. Recent measurements of positronium's 1s to 2s transition using laser spectroscopy techniques analogous to those applied to hydrogen have achieved precisions approaching parts in 10 to the power of 11. The results are consistent with the predictions of quantum electrodynamics at this precision, confirming that the electromagnetic interaction between a matter particle and an antimatter particle follows the same laws as the interaction between two matter particles. Positronium experiments also probe the quantum mechanics of annihilation, the process by which matter and antimatter convert to energy. The rate of annihilation, the angular distribution of the resulting photons, and the polarization of the photons all provide tests of quantum electrodynamics and of the symmetry between matter and antimatter in the annihilation process. Any asymmetry in the annihilation rates or photon properties between different spin configurations of positronium would be a signal of CPT violation. None has been found. To current experimental precision, the positronium results complement the anti-hydrogen results by testing different aspects of matter-antimatter symmetry in a simpler theoretical system. Together, they provide a multifaceted picture of how well the CPT theorem is confirmed by experiment, and the picture is one of remarkable consistency. Every test of the symmetry, in every system where it has been tested, at every precision that has been achieved, finds the same result. Matter and antimatter are identical, and the universe, filled with matter and almost no antimatter, continues to demand an explanation that this identical behavior does not provide. The A-trap and base experiments, and the mass of the antiproton. The alpha experiment is not the only antimatter research program at CERN. The antiproton decelerator hall hosts several independent experiments, each approaching the matter-antimatter symmetry question from a different angle with different techniques. Two of the most important are A-trap, the antihydrogen trap experiment, and base, the baryon-antibaryon symmetry experiment. The results taken together with alphas provide a more comprehensive picture of the state of antimatter physics than any single experiment could achieve. A-trap, one of the pioneering experiments in the production and study of antihydrogen, developed many of the techniques that alpha subsequently used and improved. A-trap demonstrated the first production of cold antihydrogen in 2002, simultaneously with the Athena experiment that was the predecessor of alpha. A-trap has focused particularly on the measurement of the properties of antiprotons and the energy levels of antihydrogen, using different detection techniques from alpha that provide complementary systematic uncertainties. The comparison of results between A-trap and alpha using different apparatus and different methods provides a cross-check that strengthens confidence in both sets of measurements. Base has achieved some of the most precise measurements in the field through a different approach. Rather than trapping antihydrogen atoms and studying them spectroscopically, Base traps antiprotons directly in a panning trap, a device that confines charged particles using a combination of magnetic and electric fields, and measures the cyclotron frequency and spin flip frequency of the antiproton with extraordinary precision. The ratio of these frequencies is directly related to the magnetic moment of the antiproton. The quantity that can be compared to the magnetic moment of the proton to test CPT symmetry, the base measurement of the antiproton magnetic moment, published in 2017 and refined in subsequent publications, achieved a precision of parts per billion. The result confirmed that the magnetic moment of the antiproton is equal in magnitude to that of the proton to this precision, an improvement of more than a factor of 1000 compared to previous measurements. BASE has also measured the charge-to-mass ratio of the antiproton and compared it to that of the proton, achieving similar precision. The results confirm the CPT prediction of equal masses and charges to a level of precision previously unattained. Most recently, BASE has reported a measurement of the proton to antiproton charge-to-mass ratio at a precision approaching parts in 10 to the power of 11, using a novel technique in which a single antiproton is trapped and its cyclotron frequency is measured over an extended period. This measurement is one of the most precise comparisons of any matter-antimatter pair ever achieved, and confirms the CPT prediction at a level that constrains the possible magnitude of CPT violation more stringently than any previous measurement of these quantities. The results from BASE are important not just for their precision, but for their implications. The proton is not a structureless particle. It is composed of quarks held together by the strong nuclear force, and its magnetic moment receives contributions from the quark spins, the gluon C, and the orbital motion of the quarks. The fact that the antiproton's magnetic moment matches the proton's to better than a part per billion is a test of CPT symmetry applied to the internal structure of hadrons, not just to point-like fundamental particles. It is a more demanding test because it involves the strong nuclear force as well as the electromagnetic force, and because the theoretical calculation of the proton magnetic moment from first principles is itself a significant challenge. The agreement between proton and antiproton provides a stringent constraint on CPT violation in the strong sector of physics. The cooling problem, getting antimatter to behave. One of the most profound technical challenges in antimatter physics is the challenge of cooling. Temperature in physics, there is a measure of the average kinetic energy of particles in a system. A room temperature gas contains particles moving with a wide distribution of velocities, some fast, some slow, with a characteristic average determined by the temperature. Spectroscopic measurements on a gas at room temperature are limited in precision by the Doppler effect. Atoms moving toward a laser source see the laser frequency shifted higher, while atoms moving away see it shifted lower. This Doppler broadening smears out the spectral lines and reduces the achievable precision. To perform high-precision spectroscopy on any atomic system, the atoms must be cooled, their velocities reduced to the point where the Doppler broadening is small compared to the natural line width of the transition. For ordinary hydrogen and other matter atoms, the laser cooling techniques developed since the 1980s allow the reduction of atomic velocities to micrometers per second, corresponding to temperatures in the microkelvin range. Laser cooling works by directing laser light at atoms from all sides. Atoms moving toward a laser source see the laser photons, Doppler shifted to higher frequency, closer to the atomic transition frequency. The atom absorbs a photon and gets a kick in the direction opposing its motion. The repeated absorption of photons from the laser directed against the atom's motion slows it, reducing its kinetic energy and thus cooling it. Laser cooling has not yet been implemented for antihydrogen, though this is a goal of the Alpha program. The technical challenge is that laser cooling of hydrogen requires the laser at the Lyman alpha wavelength, 121.6 nanometers, which, as discussed, is difficult to produce. Producing this laser light with sufficient power and stability to cool antihydrogen atoms in the magnetic trap would allow alpha to reduce the thermal motion of the trapped atoms, narrowing the spectral lines and dramatically improving the precision of all spectroscopic measurements. In the absence of direct laser cooling, alpha uses indirect cooling methods. The antiprotons produced by the antiproton decelerator are cooled by contact with the cold electron plasma in the trap. Electrons, being much lighter than antiprotons, thermalize rapidly with the trap environment, and the antiprotons exchange energy with them through the electromagnetic interaction, gradually cooling the antiproton population. The positrons are cooled by interaction with the trap walls and with the residual gas in the trap region, which is maintained at extremely low temperatures by cryogenic cooling of the apparatus. The resulting antihydrogen atoms are formed from relatively cold antiprotons and positrons, but they are not as cold as what could be achieved with direct laser cooling. The precision of alpha's spectroscopic measurements is currently limited partly by the temperature of the antihydrogen atoms, which smears the spectral lines through Doppler broadening. Implementing Lyman alpha laser cooling of antihydrogen would be a transformative technical advance, potentially improving the precision of all spectroscopic measurements by factors of 10 to 100. The development of Lyman alpha laser cooling for antihydrogen is one of the primary goals of the Alpha Collaboration's current research and development program. Its achievement would mark a new era in antimatter physics, enabling measurements of CPT symmetry at precisions that rival those achieved for ordinary hydrogen, and pushing the experimental constraints on CPT violation deep into the regime, where, if the symmetry is broken at a level relevant to baryogenesis, the break might become visible. The cooling problem is not a fundamental barrier. It is a technical problem being actively solved, and its solution is one of the most anticipated advances in the field. What the standard model predicts, and where it silently fails. The standard model of particle physics is the most successful theoretical framework in the history of science. Its predictions of particle properties, interaction rates, and quantum corrections have been confirmed at extraordinary precision across a vast range of energies and phenomena. The anomalous magnetic moment of the electron, calculated in quantum electrodynamics to 10 significant figures, agrees with experiment to the same precision. The discovery of the W and Z bosons at predicted masses at CERN in 1983, the discovery of the top quark at predicted mass at Fermilab in 1995, the discovery of the Higgs boson at predicted existence, if not predicted mass at CERN in 2012, all confirm the standard model's predictive power. And yet the standard model fails, silently and completely, to explain the existence of the matter-dominated universe you inhabit. This failure is not a matter of refinement. It is a fundamental deficiency. The standard model, taken as a complete theory of the fundamental interactions, predicts a universe in which matter and antimatter were produced in equal quantities in the Big Bang and subsequently annihilated each other completely, leaving a universe containing only radiation. The Standard Model contains C-P violation in the weak sector through the CK-M matrix, but the amount of CP violation it contains is many orders of magnitude too small to account for the observed matter-antimatter asymmetry. The Standard Model's version of the electroweak phase transition is not strongly enough first order to satisfy the third Sakharov condition. The Standard Model is, in a precise and quantitative sense, insufficient to explain why you are here. This failure is known. It is acknowledged. It motivates the entire experimental program at Alpha and at the LHCb experiment and at the neutrino oscillation experiments and at every other facility searching for new sources of CP violation or new mechanisms for baryogenesis. The Standard Model is incomplete. Physics beyond the Standard Model is required to explain the matter-dominated universe, and the alpha measurements are, at one level, a search for the fingerprints of that physics in the properties of antihydrogen. The specific form that the new physics might take is constrained by what alpha's measurements find. Every measurement that confirms CPT symmetry to higher precision sets a lower bound on the scale at which CPT violating new physics can operate. If CPT is violated by some effect proportional to the square of the energy divided by a new high-energy scale, the measurement of the 1s to 2s transition at 2 parts in 10 to the power of 12 constrains the new energy scale to be above a calculable threshold. More precise measurements set higher thresholds. The progression of measurements from alpha, base, and other experiments is a systematic exclusion of CPT violating new physics at successively higher energy scales. This exclusion is important because it narrows the space of viable theoretical models. Models of quantum gravity, which is known to be a regime where the assumptions underlying the CPT theorem may break down, make specific predictions for the scale and character of CPT violation. Constraining the allowed CPT violation pushes the required scale of quantum gravitational effects to higher and higher energies, thus making it increasingly clear that whatever new physics is responsible for baryogenesis either operates through mechanisms other than direct CPT violation, or operates at energy scales so high that laboratory tests of CPT symmetry at current precision cannot reach them. The Standard Model's silent failure to explain matter is the most significant known failure of the most successful theory in science. Understanding the nature and scale of the new physics required to correct this failure is one of the central tasks of experimental and theoretical physics in the current era. Alpha's measurements are providing the most precise data in antimatter physics ever obtained, and the picture they are assembling is one of extraordinary precision and extraordinary mystery. See PT violation and the theories that predict it. If CPT symmetry were violated, it would require physics beyond quantum field theory. The CPT theorem, as discussed, follows necessarily from the combination of Lorentz invariance, quantum mechanics, and locality. Violating CPT therefore requires violating at least one of these 3 foundational assumptions. The question of which assumption might fail, at what energy scale, and with what experimental signature has generated a substantial theoretical literature. One of the most develop frameworks for CPT violation is the Standard Model Extension, SME, developed by Alan Kostelecki and colleagues. The SME is an effective field theory that adds all possible Lorentz and CPT violating terms to the Standard Model Lagrangian, weighted by coefficients that parameterize the magnitude of the violation. The SME makes no specific prediction for the values of these coefficients. It provides a systematic catalog of all possible forms of CPT violation and a translation from experimental measurements to constraints on the SME coefficients. Every antimatter measurement by alpha, base, and other experiments can be expressed as a constraint on specific combinations of SME coefficients. In the SME framework, different measurements constrain different combinations of coefficients. The 1s to 2s transition in antihydrogen constrains a specific combination involving the electron and antiproton sectors. The hyperfine transition constrains different combinations. The magnetic moment measurement by base constrains yet others. The comprehensive program of antimatter measurements being carried out at CERN's antiproton decelerator is systematically constraining the full set of SME coefficients in the antimatter sector, building a detailed picture of how well CPT symmetry is confirmed across the full range of possible violation types. A different theoretical framework for CPT violation comes from theories of quantum gravity, specifically from attempts to describe physics at the Planck scale, where quantum gravity effects become significant. In some models of quantum gravity, space-time at the Planck scale is not smooth, but has a discrete or foamy structure that breaks Lorentz invariance and hence CPT symmetry. The expected magnitude of CPT violation in these models is suppressed by powers of the ordinary energy scale divided by the Planck energy, which is why it has not been observed at laboratory energies. But precise enough measurements might be sensitive to Planck's suppressed effects even at laboratory energies, if the suppression is only linear in the ratio rather than quadratic. String theory provides yet another context for CPT violation. In string field theory, the infinite tower of massive string excitations can, through quantum corrections, produce effective CPT violating terms in the low energy effective Lagrangian. The magnitude of these terms depends on the string scale and on the specific model of string dynamics. Constraints from antimatter measurements can be translated into constraints on the string scale and on specific parameters of string field theory. The theoretical landscape of CPT violation is therefore rich. Multiple frameworks predict violation at some level, and the experimental program at CERN is systematically testing these frameworks by constraining the magnitude of the allowed violation across a wide range of observable quantities. The absence of observed violation at current precision does not rule out CPT violation at a lower level. It raises the bar. And the process of raising the bar, progressively and systematically, is how physics has always narrowed the territory of the unknown, not by finding the answer immediately, but by mapping the space where the answer does not lie, until only one region remains. The matter of mass, weighing antimatter with unprecedented precision. Mass is one of the most fundamental properties of any physical object. It determines how the object responds to forces, how much energy is required to accelerate it, and how strongly it participates in the gravitational interaction. The CPT theorem predicts that every particle and its antiparticle must have exactly equal mass. This prediction has been tested for several particle-antiparticle pairs, including the electron and positron, the proton and antiproton, and the kaon and antikaon. In every case, the masses have been found to be equal to the precision of the measurement. For the proton and antiproton, the most precise comparison comes from the measurement of their cyclotron frequencies in a Penning trap. When a charged particle is confined in a magnetic field, it orbits in circles at a frequency determined by its charge-to-mass ratio and the strength of the field. By measuring the cyclotron frequency of a proton and the cyclotron frequency of an antiproton in the same magnetic field under the same conditions, the ratio of their charge-to-mass ratios can be determined with extraordinary precision. Because the charges of the proton and antiproton are equal in magnitude, by independent measurement, the ratio of their cyclotron frequencies directly gives the ratio of their masses. The Bayes experiment has achieved a comparison of the proton and antiproton cyclotron frequencies at a precision approaching 1 part in 10 to the power of 11. The result confirms that the proton and antiproton have equal mass to this precision, with no deviation from equality detectable within the experimental uncertainty. This is among the most precise comparisons of any matter-antimatter pair ever achieved, and places the most stringent available constraint on any hypothetical difference in mass between protons and antiprotons. For the electron and the positron, the mass comparison is less direct, but has been performed at similar precision through measurements of their cyclotron frequencies and G-factors in Penning traps. The Penning trap group at the University of Washington and similar experiments have confirmed the electron-positron mass equality to precisions comparable to those of Bayes for the proton-antiproton system. For hydrogen and antihydrogen, the mass comparison is more indirect. The mass of an atom is the sum of the masses of its constituents plus the binding energy contributions. A direct measurement of the antihydrogen mass with the precision needed to test CPT symmetry at the atomic level has not yet been achieved. However, the spectroscopic measurements of alpha provide indirect constraints on the mass difference between hydrogen and antihydrogen. If the 1s to 2s transition frequency is the same in hydrogen and antihydrogen to 2 parts in 10 to the power of 12, then the energy difference between these two states is the same to this precision, which constrains the possible difference in the total mass of the atom, which is approximately proportional to the ground state energy to a corresponding precision. The measurement of antihydrogen mass will eventually be achievable through the development of more precise mass spectrometry techniques adapted for neutral antihydrogen, or through increasingly precise spectroscopic measurements combined with theoretical calculations that relate transition frequencies to mass ratios. The trajectory of the field points toward achieving mass comparisons between hydrogen and antihydrogen at precisions comparable to those achieved for the proton-antiproton system, which would represent a rigorous test of CPT symmetry at the level of the complete atom rather than just its constituent particles. The charge of antimatter and why. It had to be measured directly. One of the most fundamental properties of any particle is its electric charge. The electric charge determines how the particle interacts with electromagnetic fields, how it attracts or repels other charged particles, and how it participates in chemical bonding and all the processes that make ordinary matter the complex and structured substance it is. The CPT theorem predicts that a particle and its antiparticle must have charges that are exactly opposite in sign and exactly equal in magnitude. For the electron and the positron, this has been confirmed to extraordinary precision. For the proton and antiproton, the magnitude of the charge has been confirmed by comparing their cyclotron frequencies in magnetic fields. But for a composite antimatter system, an entire antihydrogen atom, the question of charge has a different character. Hydrogen is electrically neutral. Its proton and electron have exactly opposite charges that cancel. Antihydrogen should be electrically neutral for the same reason. Its antiproton and positron have charges that should cancel exactly. If antihydrogen were not neutral, if there were any residual electric charge, however small, it would indicate either that the charges of the antiproton and positron are not exactly equal in magnitude, or that there is some new physics that creates a charge asymmetry in composite antimatter systems that is not present in their individual components. The charge of antihydrogen has been measured by alpha through a technique that uses the electric fields present in the apparatus during the release of trapped antihydrogen atoms. If the antihydrogen atoms have any net electric charge, the electric fields would deflect their paths as they move through the apparatus after the magnetic trap is turned off, and the positions of the annihilation events on the detector walls would be shifted from the positions expected for neutral atoms. By measuring the distribution of annihilation positions under different electric field configurations, any charge of the antihydrogen atoms can be detected. The result of this measurement, published in 2014 and representing the first direct measurement of the charge of any antimatter atom, confirmed that the charge of antihydrogen is consistent with zero. The measurement precision was approximately 1 part in 10 to the power of 8 of the electron charge. No charge was detected. The antihydrogen atom is electrically neutral to this precision, deconfirming that the charges of the antiproton and positron cancel each other in the antihydrogen atom, just as the charges of the proton and electron cancel in ordinary hydrogen. This measurement, while less precise than the spectroscopic tests of CPT symmetry, has a different character. It tests whether the neutrality of antihydrogen, which is a prerequisite for it to behave as an atom rather than as a charged particle, holds in practice. The confirmation of antihydrogen neutrality is both a consistency check on the CPT theorem and a practical demonstration that the antihydrogen produced and trapped by alpha is indeed a genuine atom rather than some exotic ionized system. And the measurement will be refined in future experiments as the precision of alpha's detection system improves, and eventually reaching a level where it constrains new physics scenarios that predict small charge differences between matter and antimatter atoms. What happens when antihydrogen meets light? The photoionization measurement. When a hydrogen atom absorbs a photon with sufficient energy to remove the electron entirely from the atom, photoionization occurs. The electron is liberated, the atom becomes a proton, and both the proton and the electron carry away some of the photon's energy as kinetic energy. The energy required to photoionize hydrogen from the ground state, the ionization energy, is 13.6 electron volts, corresponding to a photon wavelength of approximately 91.2 nanometers. Photons more energetic than this, in the extreme ultraviolet and soft X-ray range, can ionize hydrogen. The corresponding process for antihydrogen is photoionization into an antiproton and a positron. The ionization energy of antihydrogen is predicted by CPT symmetry to be exactly the same as that of hydrogen, 13.6 electron volts. If the ionization energy were different, it would reflect the difference in the binding energy of the positron in the antihydrogen atom compared to the electron in hydrogen, which would imply a difference in the electromagnetic interaction in the matter and antimatter sectors, or a difference in the positron and electron masses that is inconsistent with the CPT theorem. Measuring the ionization energy of antihydrogen directly requires producing photons in the extreme ultraviolet range and directing them at trapped antihydrogen atoms, which presents the same technical challenges as the Lyman alpha spectroscopy discussed earlier. An alternative approach, which alpha has explored, uses two photon processes to achieve ionization with longer wavelength photons. By using laser light at a wavelength corresponding to the 1s to 3p transition, which drives the antihydrogen atom to a high excited state, followed by ionization of the excited atom by a second photon, the ionization of antihydrogen can be achieved with visible or near ultraviolet laser light rather than extreme ultraviolet. The measurement of antihydrogen photoionization is interesting not just as a test of the ionization energy, but as a technique for state-selective manipulation of antihydrogen atoms. By driving specific transitions and selectively ionizing atoms in specific states, and alpha can prepare ensembles of antihydrogen atoms in specific quantum states for subsequent spectroscopic measurement. This state preparation capability is a tool for improving the precision of other measurements, not just for measuring the ionization energy itself. The development of state-selective photoionization as a tool in the alpha apparatus illustrates the broader point that the antimatter physics program is not a sequence of isolated measurements, but a developing experimental infrastructure where each advance in technique enables new and more precise measurements. The progression from the first trapping of antihydrogen in 2010 to the current precision of spectroscopic measurements represents more than a decade of accumulated technical development. And the next decade will bring further advances that build on the current infrastructure. The trajectory is one of progressive refinement, each measurement building on the techniques and results of its predecessors, each advance enabling the next. The role of the antiproton, decelerator in global antimatter science. The antiproton decelerator at CERN is the only facility in the world capable of producing low-energy antiprotons in the quantities and at the energies needed for precision antimatter physics experiments. It is the indispensable infrastructure on which the entire alpha program and the programs of ATRAP, BASE, ASACUSA, and other experiments in the antiproton decelerator hole depend. And understanding what it is and how it works provides context for understanding both the achievements of current antimatter physics and the constraints on its future development. The antiproton decelerator was not designed for precision atomic physics, It was designed to support the broader program of antimatter research at CERN following the shutdown of the low-energy antiproton ring, LEOR, in 1996. LEOR had been the world's first antiproton facility specifically optimized for low-energy antiproton physics, and its shutdown left the field without the infrastructure needed to continue the work it had enabled. The antiproton decelerator was built as its successor, a more compact and less expensive facility that could continue the antiproton physics program within the constraints of CERN's priorities and budget. The antiproton decelerator operates by receiving a pulse of antiprotons from the proton synchrotron, where they are produced by proton-target collisions, and decelerating them through a series of radio frequency deceleration stages and stochastic cooling, a technique that reduces the energy spread of the antiproton beam by sensing the average momentum error of the beam and applying a corrective kick, improving the beam quality. The process takes approximately a minute and a half per cycle, producing a pulse of approximately 10 to the power of 7 antiprotons at an energy of 5.3 megaelectron-volts. The addition of ELINA, the extra low energy antiproton ring, has significantly improved the antiproton supply to the experiments. ELINA decelerates the antiprotons from the antiproton decelerator further from 5.3 megaelectron-volts to 100 kiloelectron-volts, a factor of about 15 energy. At the lower energy, the fraction of antiprotons that can be captured in the panning traps used to confine them for experiments is much higher, because lower energy particles are easier to slow and stop within the trap. The commissioning of ELINA has approximately tripled or quadrupled the number of antiprotons available to each experiment per unit time. The future of the antiproton, decelerator and ELINA is tied to the future of CERN's scientific program. The facility is expected to continue operation for the foreseeable future, with ongoing improvements to the antiproton beam, quality and delivery efficiency. A proposed future facility called FAIR, the Facility for Antiproton and Ion Research in Darmstadt, Germany. They will produce antiprotons at much higher intensities than the current CERN facility, opening possibilities for antimatter physics experiments of greater statistical power. FAIR is under construction and expected to begin antiproton operations in the late 2000s. The existence of a single global facility for low-energy antiproton physics reflects both the rarity and the importance of the science. Antiproton production and deceleration is a technically demanding and expensive operation that cannot be replicated on a small scale. The concentration of the world's antimatter physics capability at one location creates dependencies, but also enables a collaborative scientific community where multiple experiments share infrastructure and techniques, accelerating the overall pace of discovery. Alpha, base, A-trap, then A, SA, C, U, SA all operate in the same hall, share technical expertise, and collectively push the boundaries of what is known about antimatter more effectively than any single experiment could alone. The Asakusa experiment and antiprotonic helium, the Asakusa experiment, atomic spectroscopy, and collisions. Using slow antiprotons pursues a different approach to precision antimatter physics from alpha and base. Rather than trapping antihydrogen atoms or measuring the properties of individual antiprotons, Asakusa focuses on antiprotonic helium, an exotic atom in which one of the two electrons in a helium atom is replaced by an antiproton. This atom, which has no ordinary matter counterpart, since it requires an antiproton in the role normally played by an electron, exists briefly before the antiproton, being much heavier than an electron, then gradually spirals inward and annihilates on the helium nucleus. The brief existence of antiprotonic helium, typically a few microseconds, is long enough to perform laser spectroscopic measurements of the atom's energy levels. The antiproton in antiprotonic helium occupies a highly excited orbit with principal quantum number around 38, meaning it is in a state much further from the nucleus than an electron in the ground state. In this orbit, the antiproton behaves like an extremely heavy, negatively charged particle, executing classical-like circular orbits around the nucleus, while the remaining electron occupies its ground state. The energy levels of the antiproton's orbit depend on the antiproton mass, charge, and the details of its interaction with the helium nucleus and the electron. By measuring the frequencies of laser-induced transitions between adjacent antiprotonic helium states and comparing them to the predictions of three-body quantum mechanics, which includes the nucleus, the antiproton, and the electron, ASACUSA can determine the antiproton mass and charge with high precision. The calculation of the energy levels of antiprotonic helium is a formidable theoretical problem, requiring the numerical solution of the three-body Schrödinger equation with high precision, but it has been accomplished at a level sufficient to allow precision comparisons with experiment. Asakusa's measurements of antiprotonic helium transition frequencies have confirmed the antiproton mass to a precision of better than 1 part in 10 to the power of 9. The antiproton mass is found to be equal to the proton mass to this precision, consistent with CPT symmetry. These measurements complement the base cyclotron frequency comparison by using a completely different physical system and a different experimental technique, providing an independent confirmation of the CPT prediction for the proton-antiproton mass ratio. ASACUSA has also developed a technique for measuring the hyperfine structure of antihydrogen in a beam configuration, as opposed to the trapped configuration used by alpha. Antihydrogen atoms formed in a positron plasma are allowed to escape from a magnetic trap in a specific hyperfine state, forming a beam, which then passes through a microwave cavity where the hyperfine transition can be driven. The atoms that undergo the transition are detected by a downstream detector. This technique provides a measurement of the antihydrogen hyperfine frequency that is complementary to alpha's measurement, using different systematics and potentially different precision. The diversity of experimental approaches in the antiproton decelerator hall, each addressing the matter-antimatter symmetry from a different angle with different techniques, is one of the strengths of the field. No single measurement, however precise, provides the complete picture. The combination of multiple measurements, each constraining different aspects of CPT symmetry in different physical systems, builds a comprehensive and mutually consistent test of the symmetry that is more robust and more informative than any individual result. What would change? If a difference were found, consider the implications of the scenario that the alpha measurements are designed but have so far failed to produce a measurement of antihydrogen that differs from the corresponding measurement of ordinary hydrogen. not by a lot, not dramatically, but by any measurable amount. Any deviation from the exact equality that CPT symmetry demands, that falls outside the experimental uncertainty. Such a result would be the most significant discovery in the history of physics. Not because of what it would explain, though the implications for baryogenesis and the matter-antimatter asymmetry would be immediate and profound, but because of what it would destroy. The CPT theorem is not a consequence of a specific model or a specific approximation. It is a mathematical necessity that follows from the most basic assumptions of relativistic quantum field theory. A CPT violation would not modify the standard model. It would make the standard model incompatible with observation in a way that requires abandoning not the model's specific predictions, but the theoretical framework that underlies it. The candidates for a post-CPT violating theoretical framework are limited and underdeveloped. String field theory, as mentioned, can accommodate CPT violation through mechanisms involving the structure of the string vacuum. Loop quantum gravity and other quantum gravity approaches predict CPT violation through the discrete structure of space-time at the Planck scale. The standard model extension provides a phenomenological framework for cataloging the observable consequences of CPT violation, but does not derive CPT violation from any specific mechanism. What lies beyond quantum field theory, in the theoretical space that a CPT violation would open, is largely unexplored territory. A CPT violation found at the precision level of alpha's current measurements at the scale of parts per trillion would be a CPT violation at a scale that is not obviously connected to any specific new physics in a way that could be straightforwardly incorporated into a revised theoretical framework. The theoretical challenge would be immense to construct a framework that preserves all the successes of the standard model, including its extraordinary predictions for electromagnetic, strong, and weak force phenomena, while accommodating a specific CPT violating term of a specific form and magnitude in the anti-hydrogen sector. The experimental challenge following such a discovery would be equally immense. To confirm the result with multiple independent measurements, to determine whether the violation is in the antiproton sector, the positron sector, or a property of the composite system, to search for related violations in other systems, and to determine whether the violation can account for the observed matter-antimatter asymmetry of the universe, or requires additional new physics. A CPT violation in the alpha experiment would not solve the problem of baryogenesis. It would transform it from a problem of finding the physics that caused the asymmetry to a problem of understanding what kind of physics produces both the observed CPT violation and the correct cosmological asymmetry. No such result has been found. Every measurement so far confirms CPT symmetry. The absence of a discovered CPT violation is not a failure of alpha or of antimatter physics generally. It is a precise and progressively tighter constraint on the allowed magnitude of CPT violation, which is itself a profound result, and the progressive tightening of that constraint, measurement by measurement, is advancing the field toward the precision at which, if CPT violation exists at a level relevant to baryogenesis, it must either become visible or be definitively ruled out. The connection to neutrino, physics, and leptogenesis. The Althea experiment operates in the quark and the lepton sectors of the standard model, measuring the properties of antiprotons which are hadrons composed of quarks, and positrons, which are leptons. The matter-antimatter asymmetry of the universe could have originated in either sector or in the connection between them, depending on which theoretical mechanism of baryogenesis is operative. Understanding how alpha's measurements connect to the broader landscape of baryogenesis mechanisms requires considering the relationship between the quark and lepton sectors. As discussed in the context of earlier videos on this topic, leptogenesis is a mechanism in which the baryon asymmetry of the universe originated as a lepton asymmetry, generated by the CP-violating decay of heavy Majorana neutrinos in the early universe, which was subsequently converted to baryon asymmetry by sphaleronic processes. Leptogenesis requires CP violation in the lepton sector, specifically in the mixing and decay of heavy Majorana neutrinos and in the mixing matrix of light neutrinos, described by the PMNS matrix. The alpha measurements do not directly test leptogenesis. Antihydrogen contains a positron, which is an antimatter lepton, but the spectroscopic measurements of antihydrogen are primarily sensitive to the electromagnetic and strong force properties of the antiproton and positron, not to the weak force properties that govern neutrino mixing. A violation of CPT symmetry found in antihydrogen would be a violation involving the strong and electromagnetic sectors, not the weak sector in which leptogenesis operates. However, the connection between alpha's measurements and leptogenesis is not entirely absent. The CPT theorem predicts exact equality between all matter-antimatter pairs across all sectors of the standard model, including the lepton sector. If CPT symmetry is violated in the quark or electromagnetic sector at any level, the CPT theorem implies that it must also be violated in the lepton sector, because any CPT violating physics that affects any sector must be incorporated into a consistent framework that also affects other sectors. The form and magnitude of the CPT violation in different sectors would depend on the specific mechanism producing it. Conversely, measurements of CPT symmetry in the lepton sector provide constraints complementary to alpha's measurements. The comparison of electron and positron properties, including their masses, charges, and magnetic moments, is another test of CPT symmetry in the lepton sector. Measurements of neutrino and antineutrino oscillation rates by experiments like T2K, NOVA, and the future Dune experiment test CPT symmetry in the neutrino sector. Any CPT violation found in one of these systems would motivate a search for related violations in others, and the pattern of violations across sectors would provide theoretical clues to the mechanism. The broader antimatter physics program, connecting alpha's measurements of antihydrogen to the neutrino oscillation measurements of leptonic CP violation, to the LHCb measurements of CP violation in B-meson decays, that constitutes a comprehensive experimental search for the asymmetry between matter and antimatter across all the sectors of physics that can be probed. The search has not yet found the asymmetry at the level required to explain the universe. But the search is the most thorough and the most precise in the history of the question, and its progress is measured in the ever-tightening constraints on where the answer is not. The philosophical weight of an exact symmetry. There is a peculiar philosophical position in which the alpha experiment now finds itself, and it is worth dwelling on. The experiment is searching for a difference between matter and antimatter, every measurement finds no difference to increasing precision. The universe we inhabit is composed almost entirely of matter, with essentially no primordial antimatter surviving. And these two facts are in direct contradiction. If matter and antimatter are identical in all properties, why does the universe contain only matter? The conventional response to this contradiction is that the symmetry must be broken, and the measurements have simply not yet reached the precision at which the break becomes visible. This is a coherent position. The precision of alpha's current measurements, extraordinary as it is, covers only a limited range of the theoretical space in which CPT violation might reside. Violations at energy scales above the range probed by alpha's transitions would not be visible at current precision. Violations of a type that affect certain quantum numbers, but not those probed by the 1s to 2s, and hyperfine measurements would also not be detected. The absence of detected violation does not rule out violation in general. But there is another philosophical position, less comfortable but equally coherent. Perhaps the symmetry is exact. Perhaps matter and antimatter truly are identical in all physical properties, and the matter-dominated universe arose not from a property of the particles themselves, but from some other mechanism entirely. Mechanisms of baryogenesis that do not require CPT violation exist in principle. If the initial conditions of the universe were asymmetric, containing more matter than antimatter from the very beginning, rather than being produced by a symmetric mechanism, then no CPT violation would be required or expected. The asymmetric initial conditions would simply be a fact about the universe, unexplained by any dynamical mechanism. This position, called spontaneous baryogenesis, or, in its strongest form, initial condition baryogenesis, does not resolve the matter of why the initial conditions were asymmetric. It relocates the question from the dynamics of the early universe to the conditions at or before the Big Bang, a domain where physics currently has no predictive framework. It is not a satisfying resolution in the sense of providing an explanation. It is a repositioning of the mystery. The philosophical weight of an exact symmetry between matter and antimatter, if it is confirmed by increasingly precise measurements, is the weight of a universe that contains only matter, but whose fundamental laws treat matter and antimatter identically. A universe that is made of one thing, but whose rules do not prefer that thing. A universe whose existence, in the form it has, this is not explained by the laws that govern it. This is not a contradiction in the logical sense. The laws govern what happens to matter and antimatter once they exist. They do not necessarily determine how much of each initially existed, but it is an unsatisfying incompleteness, a gap in the explanation of the universe that becomes more visible, not less, as the measurements become more precise and the confirmation of symmetry becomes more thorough. The future of antimatter physics. What comes after? Alpha. The alpha experiment is not the endpoint of antimatter physics. It is a milestone in an ongoing program that will continue to develop in sophistication and precision for decades. Understanding what comes after alpha, what experiments are planned, and what measurements they will attempt, provides a sense of the trajectory of the field and of how close or far we may be from an experimental resolution of the matter-antimatter mystery. The alpha collaboration itself plans a series of improvements to the existing apparatus. The implementation of Lyman alpha laser cooling, as discussed, would dramatically improve the precision of all spectroscopic measurements by reducing the Doppler broadening of antihydrogen spectral lines. The development of improved detection systems with higher efficiency and better spatial resolution would increase the sensitivity of the measurements to small asymmetries. The use of quantum electrodynamics calculations at higher order to provide more precise theoretical predictions for comparison with measurements would reduce the theoretical uncertainty in the interpretation of the results. Beyond alpha, a proposed next-generation experiment called Alpha Ultimate or Alpha G2 envisions a larger trap volume, higher antihydrogen production rates enabled by ALINA, and future improvements to the antiproton supply, and the implementation of laser cooling as a standard operational technique. This envisioned experiment could achieve spectroscopic precision for antihydrogen at a level comparable to that of the most precise measurements of ordinary hydrogen, which would represent a test of CPT symmetry at parts per 15 or better, an improvement of several orders of magnitude over current alpha results. At FAIR, the Facility for Antiproton and Ion Research, the PANDA experiment will study the properties of antiprotons and their interactions with nuclei at much higher energies than the antiproton decelerator provides, exploring the strong force sector of CPT symmetry in ways that complement the atomic physics measurements of alpha and base. The FLARE facility, proposed as a low-energy antiproton facility at FAIR, would provide a high-intensity source of slow antiprotons for precision atomic physics experiments, enabling measurements with statistical power substantially greater than what is currently achievable at CERN. In the longer term, the possibility of antihydrogen in space using the zero-gravity environment and the absence of seismic noise to achieve even higher precision measurements has been discussed in theoretical studies. The practical challenges are immense, but the potential precision improvement is significant for certain types of measurements that are limited by gravitational effects and vibration noise on Earth. The trajectory of the field is clear: higher precision, more diverse measurements, more complementary experimental approaches, and progressively tighter constraints on CPT violation across a wider range of the theoretical parameter space. And the question is whether the precision will improve rapidly enough and in the right directions to find the CPT violation that the matter-dominated universe implies must exist somewhere. If it does, it will be the most significant discovery in fundamental physics since the discovery of the Higgs boson. If it does not, the precision constraints will continue to squeeze the available theoretical space, forcing theorists toward either more exotic mechanisms or the uncomfortable acceptance that the explanation of the matter-dominated universe lies in physics that laboratory experiments cannot access. The antihydrogen in a magnetic field. The Zeeman effect. Test. When an atom is placed in a magnetic field, the degeneracy of its energy levels, the fact that different quantum states with the same energy can exist in the absence of a field, is broken. The magnetic field interacts with the magnetic moments of the electron and nucleus, shifting different energy levels by different amounts depending on the quantum numbers of the state. This splitting of energy levels by a magnetic field is called the Zeeman effect, named after Pieter Zeeman, who discovered it in 1896. The Zeeman effect has been fundamental to the development of quantum mechanics and is used routinely in atomic physics, astrophysics, and magnetic resonance imaging. For ordinary hydrogen, the Zeeman effect is described with extraordinary precision by quantum electrodynamics, including contributions from the electron spin, the nuclear spin, and the coupling between them. The energy shifts of the ground state hyperfine substates in a magnetic field are described by the Bright-Rabi formula, which gives the energies as a function of the magnetic field, strength, and the magnetic quantum numbers of the states. This formula is accurate to within the precision of the best measurements for ordinary hydrogen. For anti-hydrogen, the Zeeman effect is the basis of the magnetic trapping technique. The 4 hyperfine substates of the anti-hydrogen ground state have magnetic moments that differ in magnitude and sign. 2 of the substates, called low field-seeking states, have magnetic moments oriented such that they are repelled from regions of high magnetic field and attracted toward regions of low magnetic field. The alpha magnetic trap creates a local minimum in the magnetic field at its center, and anti-hydrogen atoms in low field-seeking states are confined there. The fact that anti-hydrogen can be magnetically trapped at all is itself a confirmation of the Zeeman effect for antimatter. If the anti-hydrogen ground state did not have the hyperfine substructure predicted by CPT symmetry, with the corresponding magnetic moments, the trapping mechanism would not work, and no anti-hydrogen would be trapped. The successful trapping of anti-hydrogen is therefore, in a sense, an experimental verification of the Zeeman effect for antimatter at the level required for the atomic structure to be consistent with CPT symmetry. A more direct measurement of the Zeeman effect for anti-hydrogen is achieved through the hyperfine transition measurements discussed earlier, which involve transitions between different hyperfine substates in a magnetic field. The energy differences between these substates, measured as a function of microwave frequency, directly reflect the Zeeman splitting of the antihydrogen ground state. The agreement between the measured Zeeman splitting and the predictions of quantum electrodynamics for antihydrogen is an additional test of CPT symmetry in the presence of external fields. Extending the Zeeman effect measurement to higher precision and to excited states of antihydrogen would provide additional tests. The Zeeman effect for the 2s state, for example, has a different structure from that of the ground state, reflecting the different magnetic moments of the constituents in this orbital. A precise measurement of the Zeeman splitting of the 2s state combined with the ground state measurement would provide a more overdetermined test of CPT symmetry in the presence of magnetic fields, constraining a different combination of fundamental constants and allowing a more comprehensive picture of the symmetry at the level of the full hydrogen spectrum. The quantum state of antihydrogen. What precision reveals. About structure. Quantum mechanics describes physical systems through wave functions, mathematical objects, whose squared magnitude gives the probability of finding the system in any given configuration. The wave function of a hydrogen atom in a given energy, eigenstate, encodes the probability distribution of the electron around the nucleus, the energy of the state, and the quantum numbers that characterize the state. These quantum numbers, the principal quantum number n, the orbital angular momentum, quantum number L, the magnetic quantum number m, and the spin quantum number s together specify the state completely within the framework of quantum mechanics as applied to the hydrogen atom. For anti-hydrogen, CPT symmetry predicts that the quantum mechanical description is identical to that of hydrogen, with the same energy, eigenvalues, the same quantum numbers, and the same wave function spatial distributions. This prediction is tested with the spectroscopic measurements of alpha. If the transition frequencies between energy states are the same in hydrogen and anti-hydrogen, the energy eigenvalues are the same, and therefore the quantum mechanical structure is identical. But there are aspects of the quantum mechanical structure of hydrogen that are tested by measurements beyond just transition frequencies. The transition rates, the probabilities per unit time for spontaneous emission from excited states, are predicted by quantum electrodynamics and depend on the overlap integrals of the wave functions of the initial and the final states. The selection rules that determine which transitions are allowed, which are forbidden, and which are suppressed by higher order processes are a consequence of the symmetry properties of the wave functions. The hyperfine structure, which reflects the coupling between the electron spin and the nuclear spin through their magnetic moments, depends on the wave function of the electron at the location of the nucleus. Alpha's measurements are beginning to probe these quantum mechanical details of anti-hydrogen beyond just transition frequencies. The measurement of transition rates by observing the time evolution of the anti-hydrogen population in excited states tests whether the spontaneous emission probabilities in anti-hydrogen are the same as in hydrogen. The observation of selection rule violations or confirmations by searching for transitions that should be forbidden in hydrogen and testing whether they are also forbidden in anti-hydrogen probes the symmetry of the wave functions under CPT transformation. These measurements are at the frontier of what alpha can currently achieve. The statistics available with current anti-hydrogen production rates limit the precision with which transition rates and selection rules can be tested. But as the production rates improve, and as the experimental technique continues to develop, these measurements will become achievable, and the quantum mechanical structure of anti-hydrogen will be tested with increasing completeness. The quantum state of anti-hydrogen is not merely an academic interest. The quantum mechanical structure of atoms is the foundation of chemistry, of biological molecules, of all the complex structures that constitute the world. If the quantum mechanics of anti-hydrogen differed from that of hydrogen in any way, it would imply that an antimatter world, a universe made of antimatter rather than matter, would have a different chemistry, different molecular structures, and potentially a different complexity of structure than the matter world we inhabit. The fact that the quantum mechanics of anti-hydrogen appears identical to that of hydrogen to every precision tested implies that the antimatter world would be chemically and physically identical to ours. The asymmetry between matter and antimatter is not in their chemistry, it is in their abundance. And the origin of that asymmetry in abundance, despite the identity of properties, remains the deepest open question in physics. The information in annihilation. What the gamma rays tell us. Every time an anti-hydrogen atom escapes the magnetic trap in alpha and strikes the wall of the apparatus, the resulting annihilation event is a source of information. The antiproton in the anti-hydrogen annihilates with a proton in the wall material, thus producing a shower of pions and other particles that are detected by the silicon vertex detector surrounding the trap. The positron in the antihydrogen annihilates with an electron in the wall material, producing two gamma-ray photons emitted in opposite directions, with energies of 511 kiloelectron-volts each. By detecting these annihilation products and reconstructing their properties, alpha can learn about the state of the antihydrogen atom at the moment of annihilation and about the dynamics of the annihilation process itself. The detection of positron annihilation, gamma rays at 511 kiloelectron-volts, is one of the primary diagnostic tools of alpha. The 511 kiloelectron-volt gamma ray energy is the mass energy of the electron or positron converted to radiation, following from Einstein's relation between mass and energy. The fact that two gamma rays are produced at exactly this energy in opposite directions is a direct consequence of conservation of energy and momentum during the annihilation of an electron-positron pair at rest. If the pair has some residual kinetic energy at the moment of annihilation, the gamma rays are slightly boosted in energy and are not exactly opposite in direction, but for the low energy annihilation events in alpha, these corrections are small. The angular correlation of the two annihilation photons is sensitive to the quantum state of the positronium atom that briefly forms when the positron captures an electron from the wall material before annihilating. For singlet-state positronium, the two photons are emitted at exactly 180 degrees. For triplet-state positronium, 3 photons are emitted rather than 2, and the angular correlation is different. By measuring the angular correlation and the photon number, alpha can in principle determine the fraction of positron annihilation events that proceed through singlet versus triplet positronium, which tests the quantum mechanics of positronium formation and annihilation in antihydrogen interactions. The antiproton annihilation products, the pions, and other particles produced in the antiproton nucleon annihilation carry information about the strong force interaction between the antiproton and the nucleons in the wall material, the multiplicity of pions, their charge distribution, and their angular distribution are all governed by quantum chromodynamics and reflect the internal structure of the interacting particles. By analyzing the annihilation vertex topology, the spatial pattern of particle tracks emanating from the point of annihilation, alpha can distinguish antiproton annihilation events from other background events, and can measure properties of the strong force interaction in the antimatter sector. The information extracted from annihilation events is not only a tool for counting how many antihydrogen atoms were trapped, it is a source of physics in its own right. The study of antiproton annihilation at very low energies characteristic of alpha's trapped antihydrogen, probes the strong force in a regime where the perturbative calculations of quantum chromodynamics are not applicable and where low energy effective theories must be used. Drift comparisons of antiproton annihilation with proton annihilation at the same energy would test CPT symmetry in the strong force sector independently of the spectroscopic measurements. This program is complementary to the spectroscopy and will become more accessible as the antihydrogen statistics in alpha improve. The question that remains, after every measurement, Every measurement our alpha has performed has found the same result, expressed in different ways and tested at different levels of precision. Antihydrogen is indistinguishable from hydrogen. The mirror image of the simplest atom in the universe behaves, in every way that can currently be measured, identically to its original. The laws of physics that govern antimatter are, to the precision of the best current experiments, the same laws that govern matter. And you exist in a universe made entirely of matter. These two facts sit alongside each other without resolution. The precision of the confirmation of their coexistence increases with every new measurement. The 1s to 2 s transition confirms it at 2 parts per trillion. The hyperfine transition confirms it at parts per billion. The gravitational measurement confirms that antihydrogen falls downward just as matter does. The charge measurement confirms that antihydrogen is electrically neutral. The antiproton magnetic moment, measured by Bates, is equal to the proton magnetic moment, to better than a part per billion. Every physical property of antimatter that can be measured is the same as the corresponding property of matter. And yet here you are, and there is no antimatter. Not primordially, not in equal abundance, not in any quantity detectable on cosmological scales. The universe is matter, almost exclusively, and the laws that govern that matter treat antimatter with the same formalism, the same forces, the same quantum mechanics. The asymmetry is not in the laws, or at least not at any precision currently measurable. The asymmetry is in the universe, in what exists, in what survived. The alpha experiment has not solved the problem of the matter-antimatter asymmetry. It has made the problem sharper, more precisely characterized, and more constrained in its possible solutions. It has eliminated certain classes of CPT violation, pushed the energy scale of any possible violation higher, and confirmed that the known physics of electromagnetism, strong force interactions, and gravity treat antimatter identically to matter at the precision of current experiments. What remains is the question itself, unresolved, more precisely unresolved than at any previous point in the history of science. The question of why you exist, phrased in the most physically precise terms available, is not answered by the most precise measurements ever made of the substance that is your mirror image. The mirror shows you your reflection exactly in every detail, and you look at it and you wonder why you are there, and it is not. The apparatus is running, the data is accumulating, the precision is improving, and the universe, made of something instead of nothing, continues to withhold its most fundamental secret from the instruments designed to find it. The Alpha experiment sits in a hole beneath the surface of the Earth near Geneva, Switzerland, surrounded by thousands of tons of infrastructure built by hundreds of physicists over decades, dedicated to the study of a substance that cannot touch its own container without vanishing. The antihydrogen atoms it produces live for fractions of a second. The measurements made on them test the laws of nature at a precision that would have been unimaginable a generation ago. And every measurement confirms, with increasing force, what every previous measurement has confirmed: antihydrogen is hydrogen. The mirror world is indistinguishable from this one. You carry the consequence of this result in every atom of your body. Every proton in your cells is a survivor. Every electron in every molecule is a remnant of a process that should have erased it. the universe in which you exist, the only universe you can ever inhabit, is a universe that the laws of physics, as currently understood, do not explain. The matter that constitutes you should not have outlasted the antimatter that accompanied it. The measurements of alpha confirm with increasing precision that there is no known reason it did. This is not a failure of science. It is a situation science has arrived at after decades of increasingly precise inquiry, a precise and verified description of what exists, combined with an incomplete and unverified explanation of why it exists. The two parts of physics, the observational and the explanatory, are not yet fully connected for the most fundamental fact about the universe. The search continues, the precision improves, the constraint on the answer tightens, but the answer itself remains outside the reach of any current measurement, somewhere in the physics that the instruments have not yet been built to probe, or somewhere in the theoretical framework that has not yet been written. The atoms in your body are waiting for an explanation that physics has not yet provided. So is the field.